and we have a couple of talks. One is from an atmospheric perspective, and we'll address the synergy between clouds over Greenland and the surface energy budget. And then we have another presentation from the glaciers and sea level perspective on ice mass balance over the Greenland ice sheet and drivers of changes there. So Jan, are you presenting first?
Yes, that's correct.
Okay, so our first speaker is going to be Jan Lenaerts, and he is going to speak from the glaciers and sea level collaboration team perspective. And I think with that, we'll just get started with your talk and then follow that with a discussion session and move on to the next. So Jan.
Okay, thank you. Welcome everyone. I'm starting to share my screen now, so that should work. There we go. Okay, so I'll be talking today a bit on our work we're doing on understanding the interactions between atmosphere and the ice sheet surface over the ice sheets, but in particular over Greenland. And I will touch upon a combination of in situ observations, some remote sensing, and in the end some climate modeling. So I'm Jan Lenaerts. I'm actually right now in the transition between Europe, Utrecht University, to the US, where I'll be starting at the University of Colorado just next month. So as you all know or should know, the Greenland ice sheet is losing mass. And it hasn't been losing mass for a long time, only since the, let's say, mid or late 1990s. And this is shown here by the red line. Just look at the y-axis showing the 0 line here. And the red line is basically the mass balance. So when it's positive, it means that the ice sheet is gaining mass. When it's negative, it means that the ice sheet is losing mass. And you can see it basically hovers around this 0 line for most of the period prior to 1990. And then you can see this regular decrease in time after. Right now we're at a mass balance of around minus 250 gigatons per year. But as you can also see in this red line, there's a huge variability from year to year. Even when there is no trend prior to the 1990s, you can see that the mass balance varies a lot from year to year, several hundreds of gigatons, and that's a lot. And if you compare or put this in the perspective of where this comes from, this variability, and also the trend is highlighted by showing the blue line here on top, which shows basically the ice discharge from the Greenland ice sheet. So the amount of ice that is lost by the glaciers. And the orange line, which is the mass input, we call that the surface mass balance. And this is basically the main variable we're looking into. And you can see if you compare the orange and the red line, that the variability and also the trend is very, very comparable, which means that much of the mass balance is governed by surface mass balance. And also the recent change in mass balance, the red line here, is governed by a change, by a decrease in surface mass balance. So there is less mass input onto the Greenland ice sheet. And this is, if you put this in numbers, around more than 60% of this change in mass balance that can be explained by the surface mass balance. So as a conclusion and as a motivation of our work, of course, is we should understand the surface mass balance and the drivers of the surface mass balance in more detail. And this is what we're trying to do. And one important aspect of this is trying to understand the interactions between the energy that is received by the ice sheet surface and the mass that is received by the surface. And one important component of this interaction is the surface melt. So The surface energy balance is basically the amount of energy that is received by the surface. And when it's summer, the temperature can reach the melting point, and any excess energy that is available at that time, that will be used for surface melting. And surface melting is nothing else than the production of liquid water at the surface. And when this liquid water does not refreeze in the snowpack, it will run off, and it will basically lead to a surface loss term in the surface mass balance, and that's called the runoff. So the surface mass balance is governed by the surface melt, which is in turn governed by the surface energy balance. And I'd like to point out some of the ongoing interactions. Oh, sorry, I have a chat here, so okay, sorry, this is not important. Let's go back. Some of the important drivers of this energy and mass exchange on the Greenland ice sheets, and this is shown here on the left as well as on the right. One important component I'd like to touch upon, and also Nate in the next talk, is the importance of clouds, because clouds not only determine the amount of radiation, which of course then determines the surface energy balance, but also of course determines how much snow is falling on the ice sheet, and that is of course the main source of input on the ice sheet surface. So the input term of the surface mass balance. Surface melt, on the other hand, as I was mentioning before, leads to surface runoff if the water does not refreeze, and this runoff determines the hydrology of the ice sheets. Things like the Fern aquifer that we have discovered a few years ago, supraglacial lakes, these kind of features are really driven by the surface melting and surface runoff. And ultimately, the hydrology is also driving, in part, the dynamics of the ice on the ice sheet, because water at the bed coming from the surface can lubricate the ice and can speed up the flow of the ice sheet. So these red things here that I denoted clouds, but also albedo, which I won't touch upon, but it's in a very important variable, as well as hydrology. These are really the emergence research teams. And I will basically focus on clouds here, as well as Nate in the next talk. But first, let me briefly tell you something about how important field observations are. Field observations are important to understand certain processes. And one of these important processes is blowing snow. Blowing snow is a process we don't really understand because there are so few observations available. And that led us in 2012 to go into the western part of the Greenland ice sheet, which you can see here. So this is the region where we are focusing on. And on this western part of the Greenland ice sheet, we have an array of weather stations. And on this S10 location, which is in the accumulation zone, we installed this blowing snow setup. This blowing snow setup was measuring all sorts of atmospheric conditions, as well as surface conditions, as well as blowing snow itself on the ice sheet. And this is just showing an animation of different, of just a temporal animation during the month of September, October, and November, and so on, in 2012. And you can see so much going on. There are so many interactions between the atmosphere and the surface going on. And these kind of interactions are really so small scale that you can't really either observe them from space or model them. So we really need to go into the field to understand these kind of processes. But of course, going to the field is challenging. It's challenging because it costs a lot of money. It's challenging because you can only go to one place at one time, and you can usually not stay for very long. So monitoring processes, atmospheric processes from the ground, and the interactions between atmosphere and the surface is challenging. And that also counts for clouds. The instrumentation to measure clouds is expensive, and we need usually long-term monitoring to understand certain regimes, cloud regimes, and what they do to the surface energy balance, instead of very short, usually short campaigns that give us a snapshot of what happens, but doesn't really say anything about the climatology of clouds. And also, we of course only look from below, while we would of course ideally have a three-dimensional view. Of course, there are very important local field observations, in situ observations going on Greenland. And one of the most important locations is Summit, maybe the most important. And that's what Nate will be talking up next. But what I will be touching upon is the interesting application of satellite remote sensing. Because satellite remote sensing, unlike field observations, gives us a coverage of the full ice sheet and also outside of the ice sheet for the entire globe. Here I use NASA's A-Train observations, CloudSat and Calypso, which contain both a radar and a laser, so they can look from above and give a view, a three-dimensional view of the clouds, both the very deep clouds as well as the very thin clouds. And these cover a period of 2007 to 2010, when both CloudSat and Calypso were still active. And these kind of observations give us a unique view on the climatology of clouds, only for a few years, but still. They show us that both cloud ice on the top left here in A and cloud water is occurring very frequently on the Greenland ice sheet. Ice water clouds occur more than half of the time for basically the entire ice sheet, apart from the north. And also water clouds, which are so important for the surface energy budget, occur frequently, mostly on the edges of the ice sheet, the southeast as well as the northwest. And if you look at the water path, which is basically the vertically integrated amount of ice here on the left and water on the right, you can see that there is ice and water in the clouds over all of the Greenland ice sheet, and most clearly in the regions where also the precipitation is highest in the southeast. But what these clouds also, these remote sensing observations also show us is how much radiation is received from the atmosphere by the ice sheet surface. And that's a very interesting application of these CloudSat Calypso observations. And in turn, we can use, again, these field observations from automatic weather stations, AWSs, to then evaluate how well this remote sensing product does. And this is shown in this plot here with the long wave downwelling flux on the left and the short wave downwelling flux on the right. And these show monthly mean fluxes at different locations, station locations on Greenland, with Summit here shown here for both of them. And you can see that the satellite product on the y-axis does very well in comparison with the stations on the x-axis for monthly mean fluxes, both from the long wave as well as the short wave spectra. So we can basically use these products now to understand what clouds do for the surface energy budget. And this is shown here, and mostly focus on the purple line here. The purple line shows what the cloud radiative effect is, which is basically the net amount of energy that is due to clouds. So when it's positive, it means that the clouds have a positive energy effect. They will increase the net annual mean surface energy balance at the surface of the ice sheet. And you can see in this purple line that it's basically positive everywhere, and it increases with increasing liquid and ice water path in the clouds, which means that the deeper and the more clouds you have, the more energy will be received by the ice sheet surface. And it's positive everywhere, not only in one particular region. No, it's positive everywhere, and especially along the edges, but also in the regions like summit, where it's still 20 to 25 watts per square meter in the annual mean. And what does that mean for the surface energy balance, for the surface melt, and then in the end for the surface mass balance? Well, that's shown in this slide. We used this satellite product and combined this with a climate model and a snow model to isolate the radiative effects of clouds. So what we basically did, we removed the clouds and then looked what the surface energy balance would look like and what the surface mass balance would look like. And what you can see here, these are three individual years, 2008, 2009, 2010. And the y-axis shows mass. This is in gigatons per year. And the full bars show the amount of melt. And what you can see in the three different situations: clear sky, so no clouds, no liquid clouds, or the default situation where we have clouds, we don't see a difference in the total amount of melt in the three individual years. These three bars are more or less the same. But what you can see, if you look at these more visible parts of these bars, that the amount of runoff is actually increasing if you go from clear sky to all sky, which means that the clouds actually have a tendency to increase the amount of runoff. And the reason for that is that although the amount of melt is the same, there is a reduction of the amount of refreezing, especially in parts of the day where the sun is low, during the evening, during the night, when the long wave cloud effect is dominating. And this is a very substantial effect. This is 56 plus or minus 20 gigatons per year additional runoff attributed to clouds. We can use these remote sensing data also to evaluate models, and that's a very, very powerful tool. This shows this amount of liquid water path and ice water path in the CloudSat Calypso observations here. This is the seasonal cycle over Greenland. And then all these symbols here show the difference in different data sets with the color coding here in comparison with CloudSat Calypso. And what you can see that both for liquid and for ice water path, there are substantial differences between the observations from CloudSat Calypso and different reanalysis data sets, ERA Interim, MERA2, as well as the CMIP5 models. But also that there is a substantial disagreement in the observations themselves, because we compare CloudSat Calypso here in black with the CIRAS product in gray here. These gray triangles show CIRAS. And you can see both from liquid and from ice that there is a very substantial disagreement between the observational data sets. So there's definitely, in these very subtle cloud regimes, there is definitely need for improved observations and improved algorithms to actually detect them. And then the final part of my talk is on the climate modeling. And first of all, I'd like to touch upon the tool we are using in Utrecht, which is the regional climate model RACMO2. This RACMO2 model aims to simulate all SMB components. And for that, it needs a combination of an atmospheric model with dynamics as well as physical schemes, and also with a certain forcing. And this forcing is applied here at the lateral boundaries of a regional domain, in this case, focused on Greenland. This forcing comes usually from reanalysis products or from global climate models if we're going into the future. But also very importantly is that this atmospheric model is coupled to a snow model that considers snow processes such as albedo, very important, surface melting, and how much of the surface meltwater refreezes or runs off, and also the amount of compaction of snow at the surface. And this regional climate model is, of course, very importantly, evaluated with remote sensing as well as field observations. And using these kind of field observations and remote sensing, we can come up with these very interesting products. For instance, this is the newest one. This is a downscaled surface mass balance map of Greenland for the period 1960 to 2010. With red showing negative surface mass balance, where there is more runoff than snowfall, and blue, where the largest part of the ice sheet, where there is still more snowfall than runoff. And these yellow points here on the map show all in situ observations of surface mass balance. So again, we use in situ observations to evaluate the regional climate model. And these kind of products are really, really interesting to use to understand Greenland ice sheet SMB, not only from an integrated perspective, but also on smaller scales. But of course, the downside of a regional climate model is that it's only forced by a certain atmospheric state at its lateral boundaries, because it's regional, it has a regional domain. So it doesn't see, basically, it doesn't interact with the rest of the climate system. In contrast, of course, if you couple a climate model with in all different respects, you can let part of the climate system, such as the Greenland ice sheet, interact with the rest of the global climate system. And this is what is done in the community Earth system model, where I'm also a part of. And this community Earth system model is organized in different working groups. And one of these is the Land Ice Working Group, where we try with, in collaboration with NCAR and different US institutions, as well as European institutions, to improve the representation of the Greenland ice sheet in the community Earth system model, as well as couple it to the rest of the climate system. And again, I want to stress that observations are so important, not only for evaluation of these kind of models, but also to improve them. And this is again touching upon the Klaus Hut Calypso observations. Here shown the liquid water path from these observations in comparison with an older version of the atmospheric model of this community Earth system model. And what is very clear is that there is basically zero liquid water path on most of the Greenland ice sheet in this atmospheric model. Of course, in contrast to the observations, which you have seen before. So we can use these observations to improve processes in the atmospheric model to allow for more liquid water in the clouds. And this is very important, as we have seen for the representation of the surface energy balance. And these global climate models are also, of course, vital because they give us an insight into future scenarios, also for Greenland surface mass balance. And this is a result from the community Earth system model, a previous version, with the historical surface energy balance from surface mass balance, I'm sorry, from Greenland ice sheet in the y-axis versus the global mean temperature anomaly. So in the historical period, of course, this hovers around 0. But then if you go into the future, according to different scenarios, low warming scenario, these are the blue circles, and then a high warming scenario, the red triangles show a decrease of Greenland surface mass balance with global warming. And this decrease is very, very fast as we go beyond 2 or 3 degrees warming relative to the historical period. And this is driven by, of course, by more surface melting, by increased surface energy balance, more surface melting, and as a result, more surface runoff. So also very important component of these global climate models is to resolve these kind of processes, to resolve snow processes such as snow percolation, snow refreezing, compaction, and surface runoff as a result. And I think that's my last point of interest, is that this global climate model development is very important, including snow models in these kind of coupled models. So just one slide to finish is I want to stress some, I think, very important future research venues, is that we should do or could do dedicated observational campaigns, such as the AWARE campaign that has been going on West Antarctica. Of course, Summit, as you will see in Nate's talk, is a very, very interesting data set, and I think this continued support will be very important. Another interesting and important future venue is these active satellite remote sensing, such as CloudSat Calypso, which will give us an even better insight into clouds and their radiative impact. And things like UAVs, which give us on very, very high resolution insight in surface processes and surface atmosphere interactions. And then in terms of climate model development, I think we're taking big steps in terms of resolution, where we can go down to 1 kilometer now. But of course, global climate models are not there yet. But we will get there at some point, I'm sure. And then of course, in terms of development from a physical perspective, I think both improving the snow model to consider snow processes, as well as the atmospheric model, and then most importantly clouds, will be very important in the future. Thank you.
Great, thank you, Jan. That was very interesting. Do we have questions for Jan? Well, I could start off with a question or two while everyone else is thinking. So it seems like there's a bit of discrepancy in the observations we have, especially of clouds over the ice sheet. And here on your last slide, you point out some future activities. What do you see as really critical to evaluating these remote sensing products that we have and these reanalyses that give us the spatial distribution?
Yeah, so I think there's definitely a chain that should be followed in that respect. And I think, therefore, again, weather stations and high quality weather observations, so radiation observations, but also cloud observations from Summit, for example, are, I would say, more than essential, because they give us the only ground truth that we have over the ice sheet and also outside of the ice sheet. So I think these are very essential. And then if we can show with certain confidence that the algorithms from the remote sensing work, then we can use these kind of products to evaluate reanalyses, because we clearly see that there is a lot of discrepancy between the satellite remote sensing observational products and the reanalyses products as well. So people tend to, credit reanalyses for truth, but we should be very important in very cautious in putting too much confidence in how they resolve clouds, for instance, and surface energy balance components over ice sheets.
Questions for Jan?
Yeah, this is Matt Shoup. I have a question. Jan, that was a great presentation. You showed this comparison of the surface radiation that was derived from the satellites, and I believe that is based on measurements from CloudSat Calypso that are then used to compute the surface fluxes using a radiative transfer algorithm. And I was actually, I was interested to know from you, how are these AWS radiation measurements, how are they processed? Because I know those are made autonomously, and I was actually really surprised to see such good agreement in general, and surprised also to see, you know, from the shortwave side, probably the worst agreement at Summit, where we actually have people there to maintain those measurements. And so I just, you know, can you speak a little bit to how the data is handled that is obtained autonomously, and how you can arrive at such a good agreement?
Yeah, thanks, Matt. Of course, these weather station data are autonomous. And that's a problem. So it should be thoroughly quality controlled prior to actually using it. And so one important component of that is actually before employing these things in the field, you should be very confident that the radiation measurements are actually correct. And there are certain Vaisala, for instance, derived algorithms for that. So you can basically make sure that your radiation measurements are as good as they are. And actually, these instruments are very expensive, but they're very good if you compare them to multispectral observations, for instance. They are very very high quality. So I would say there are two important aspects, like preparation, make sure that the instrument is actually doing what it should do, and then post processing is also very important. So, and there are certain ways to do this, certain algorithms to do this. Of course, throwing away data is a very regular thing to do. Not every station works as it should work. That's why you see so little points on these plots, because there are so few months actually available that have a full coverage, because these are monthly mean data. So I mean, yeah. So I think that's what I can say.